This video lecture is on projectiles at angles. I'm Mrs. Estock. Let's get started. In this unit, we've been talking about two-dimensional motion, meaning that it's an object moving in both the horizontal and the vertical direction at the same time, just like Michael Jordan here doing his famous airwalk. So when MJ is in the air, he's a projectile moving with both horizontal and vertical velocity, which is motion under the influence of gravity. And now that we're looking at motion that moves simultaneously in the horizontal and vertical directions, we need to review our vector components. Earlier in this unit, we talked about vectors that are pointing at an angle as having both a horizontal component and a vertical component. So here we're making our right triangle, where the resultant vector is the hypotenuse, and the components are the two sides of the right triangle. And also keep in mind that the direction of your resultant vector we find as an angle called theta. In this case, the example is showing a soccer ball being kicked at an angle, where we have a resultant velocity that's a combination of its two components, the horizontal and vertical velocities. In other words, if you add together graphically the two vector components, the horizontal velocity added head to tail to the vertical velocity, the resultant motion or speed that you get is the hypotenuse of that right triangle. To solve for the sides of this right triangle, we can use sine to solve for the vertical component, and we can use cosine to solve for the horizontal component. These two equations for the components are located on the back page of your reference table. Well, why will this be important when looking at projectile motion for objects launched at an angle? If you have an object that's launched at an angle, that resultant velocity must be comprised of a horizontal and vertical component. In other words, if we add those two velocity components head to tail, we get our resultant velocity. And we know from our previous lesson that as a projectile travels through its trajectory, the horizontal velocity stays the same. So here I'm representing the horizontal velocity with a red arrow, but in this case, the vertical velocity is changing. On the way up toward the peak of its trajectory, the vertical velocity decreases until the projectile reaches its peak. At peak, the vertical velocity is equal to 0, meaning that the projectile is only moving horizontally at this moment. Then, as the projectile begins to move downward, we again see a combination of the horizontal and vertical components to its motion, where the horizontal velocity still stays the same, that red arrow hasn't changed at all, but now our vertical velocity is increasing in the downward direction as it falls. If we take another look at this type of motion, Let's say we have a person that throws a ball with an initial vertical velocity of 30 meters per second and an initial horizontal velocity of 5 meters per second. It's the combination of those two vector components that result in this parabolic or smoothly curved trajectory of the projectile. And notice throughout its motion that horizontal velocity vector stays the same. It's the vertical velocity that changes due to the influence of gravity. The horizontal velocity will remain constant throughout its motion. In other words, the horizontal velocity, or Vx, is 5 meters per second everywhere. At any time, it's 5 meters per second everywhere. And at the top of the projectile's flight, the overall velocity is only in the horizontal direction because the vertical velocity will be 0. As for the vertical direction, we see a change in velocity due to the acceleration of gravity, which is, of course, 9.81 meters per second squared downward. If we think back to the direction of vectors as influencing the motion of an object, whether it's speeding up or slowing down, as this projectile moves from launch to peak, so on its way up, the velocity is decreasing because while the velocity is positive, pointing upward, the acceleration is negative, pointing downward. And when those two vectors point in opposite directions, we know the velocity will have to decrease. However, on the way down, the velocity is pointed downward as well as the acceleration. So that means that the object must be speeding up or increasing its velocity. Also notice that for the vertical direction, the velocity at peak or at the top of that parabola is equal to 0. That's that moment vertically where the object briefly pauses in the vertical direction, where that peak vertical velocity is 0. And back to our vector components. If we wanted to take these two components and recombine them to figure out the overall resultant velocity, we could by making our right triangle. So if we were asked to solve for the overall resultant velocity of a ball that lands with a horizontal velocity of 5 meters per second and a vertical velocity of 30 meters per second, what would that look like? Well, we can add our vectors head to tail as we've practiced before, and then solve for the resultant's magnitude, or the length of that hypotenuse, as well as the direction as an angle theta. To solve for the hypotenuse, we could do Pythagorean theorem, a squared plus b squared equals c squared. And in doing that, we can solve for the magnitude of the resultant velocity as 30.4 meters per second. And we can use trig to solve for the direction of that resultant velocity. Here I'm solving for theta using tangent as my trig function. Theta is equal to the inverse tan of opposite over adjacent, which is equal to 80.5 degrees. So my final answer for the overall resultant vector would be 30.4 meters per second at 80.5 degrees below the horizontal. Now that we know how to solve for the components, we're going to practice creating tables for word problems using projectiles launched at an angle. You'll find that the setup for these problems is very similar to when we were doing projectiles launched horizontally, except for one key difference. Now we have to solve for the components before we plug anything into our tables. Let's say that a ball is thrown from the ground at 20 meters per second at an angle of 60 degrees above the horizontal. How far has it traveled horizontally before hitting the ground? Well, if we draw our diagram, we can see that we have a velocity pointing at an angle of 60 degrees that has a length of 20 meters per second. And the first thing you need to do with these types of problems is solve for the components of that resultant velocity. So first I'll solve for the horizontal component. using cosine. So the horizontal velocity is equal to the resultant velocity multiplied by cosine of our angle theta. So if I take 20 meters per second times the cosine of 60 degrees, I get a horizontal component of 10 meters per second. I also have to solve for the vertical component of this resultant velocity by taking the resultant multiplied by sine theta. And here I get 17.3 meters per second as the initial vertical velocity. So now that we've solved for the components of the resultant velocity, what do we do with them? Well, now we have a horizontal and vertical velocity, two different values that we can use in our horizontal and vertical tables. So just like before, we're going to create one table for the horizontal direction and one table for the vertical direction. And notice when we put these numbers into our table, you cannot use 20 meters per second. You cannot use the resultant velocity. You have to plug in the components that we just solved for. So here, when making my tables of values, in the vertical direction, we do not know the vertical displacement, but we do know the initial vertical velocity, which is the component that we just solved for, as 17.3 meters per second. The final vertical velocity at the end of that parabola, right before it lands, will be the same magnitude, but the opposite direction as the initial vertical velocity. The acceleration is due to gravity, and we do not know the time the projectile spends in the air. For the horizontal direction, the question is asking us to solve for the horizontal displacement. We're not actually going to do that here. We're just practicing setting up the tables. For the initial horizontal velocity, this is equal to the horizontal component that we just solved for, 10 meters per second. And with the horizontal direction, just like we saw before, the initial and final velocities will be the same because the acceleration in the horizontal direction is equal to 0. And time is unknown. So this would be the setup for a problem like this. Solving for the components, drawing your diagram, setting your directions as positive, and creating your tables of values. Now let's try seeing a problem all the way through. So this problem we are going to solve for as well as setting up our tables of values. A cannonball is fired at an angle of 30 degrees to the horizontal with a velocity of 30 meters per second. So here we're being given a resultant velocity. We have to solve for how long the ball is in the air, or the time the ball is in the air, and how far it travels in the air. Let's start by drawing a picture and assigning our directions as positive. Here we have an initial resultant velocity of 30 meters per second pointing at an angle of 30 degrees. This will have a horizontal component and a vertical component to its motion, where again we can use cosine to solve for the horizontal side of our right triangle, and we can use sine to solve for the vertical side of our right triangle. In doing so, we get a horizontal component of 26 meters per second and a vertical component of 15 meters per second. These are the values that we're going to use in our tables in the next slide. So now if I start filling in my tables, I don't know my vertical displacement, but I do know the initial vertical velocity is 15 meters per second up. My final vertical velocity will be negative 15 meters per second, or 15 meters per second down. The acceleration is due to gravity, and I'm looking to solve for time. In the horizontal direction, we will eventually solve for the horizontal displacement. We know the initial horizontal velocity is equal to the horizontal component we just solved for, 26 meters per second. The horizontal velocity stays constant because the horizontal acceleration is 0. And time, again, is unknown. So now, using these two tables of values, we're going to first solve for the time this projectile is in the air. Whenever you're solving for time, it's best to use the vertical direction. And that's because in the horizontal direction, the acceleration is 0, which tends to cancel out some of the key values you're looking to solve for. So to find time, we're going to use that vertical table of values. I'm going to choose to use this equation, VF equals VI plus AT. If I rearrange it slightly to solve for time, time will be equal to final minus initial velocity divided by acceleration. And when I plug those values into my equation, I have negative 15 meters per second minus 15 meters per second, which will end up being negative 30 meters per second, divided by a negative 9.81 meters per second squared, which gives me a time of 3 seconds. So this is the total time the projectile spent in the air. And last but not least, we're going to solve for the horizontal distance traveled by the projectile, or the range of the projectile. So remember, range was one of your vocabulary words. Range just means the horizontal distance traveled. For the horizontal distance traveled, we're only going to use the information from the horizontal table of values. However, you may notice that time is equal to 3 seconds. That's the time we just solved for. But even though we use the vertical direction to solve for time, we can still use that same value in the horizontal table. The reason for that is because time is a scalar quantity. So if the time was 3 seconds in the vertical direction, it will also be 3 seconds in the horizontal direction, because time does not have a direction associated with it. To solve for the horizontal distance or displacement, I can use the equation d equals VIT plus 1/2 AT squared. And since the acceleration horizontally is 0, this whole second half of the equation will simplify to 0. So now I'm left with dx equals VI times t. I'm plugging in the horizontal velocity of 26 meters per second multiplied by the time of 3 seconds to get a range or horizontal displacement of 78 meters.